Welcome back to Module 1. In our last lecture, we explored semiconductor band theory. We learned how continuous energy bands form, what the band gap is, and how Fermi-Dirac statistics help us predict the population of electrons and holes. However, we ended with a critical problem. If we take a pure, perfectly intrinsic semiconductor and shine light on it, we will successfully generate electron-hole pairs. But those charges will just wander around randomly until they eventually bump into each other and recombine, losing their energy as heat. A pure semiconductor cannot generate usable electrical power because it lacks a directional driving force. To create a solar cell, we must force the photo-generated electrons to move in one direction and the holes to move in the exact opposite direction. We need to build structural and electrical asymmetry directly into the crystal lattice. Today we are going to learn how to engineer this asymmetry through a process called doping, which allows us to create the absolute heart of the solar cell, the p-n junction. To break the symmetry of our material, we intentionally introduce specific impurity atoms into the pure crystal lattice. This process is called doping, and it turns our pure, intrinsic material into an extrinsic semiconductor. Let us look at two types of doping. First, we have n-type doping. If we introduce an atom that has one more valence electron than the host atoms, known as a donor impurity, that extra electron cannot tightly bond into the lattice. It requires very little thermal energy to break free and enter the conduction band. Because we are adding negative charge carriers, we call this an n-type material. In an n-type semiconductor, electrons are the abundant majority carriers, and holes are the scarce minority carriers. Conversely, we have p-type doping. Here, we introduce an atom with one fewer valence electron than the host, an acceptor impurity. This missing electron creates a void, or a hole, in the valence band. Other electrons easily hop into this void, effectively allowing the positively charged hole to move freely through the crystal. Because we are adding positive charge carriers, this is a p-type material. Holes are now the majority carriers, and electrons are the minority carriers. When we dope a material, we drastically shift its thermodynamic equilibrium. According to the mass action law, under thermal equilibrium, the concentration of electrons multiplied by the concentration of holes always equals the square of the intrinsic carrier concentration. This means if we drastically increase the electrons through n-type doping, the number of holes must proportionately collapse. Visually, on our energy band diagram, doping shifts the Fermi level. In an n-type material, the Fermi level moves up, resting just below the conduction band. In a p-type material, the Fermi level moves down, resting just above the valence band. Now for the crucial step. What happens when we bring a p-type material and an n-type material into intimate physical contact? At the exact moment the junction is formed, we have a massive concentration gradient. On the n side, we have an ocean of electrons. On the p side, there are almost none. Just like a drop of ink diffusing through a glass of water, physics dictates that particles will move from an area of high concentration to an area of low concentration. Electrons immediately begin diffusing across the junction from the n side over to the p side. Simultaneously, holes diffuse from the p side over to the n side. This movement of charge, driven by a concentration gradient, is called the diffusion current. But this diffusion cannot continue forever. When an electron leaves the n side, it leaves behind the donor atom that provided it. Because the electron took a negative charge away, that stationary donor atom is now a positively charged ion, fixed securely within the crystal lattice. Similarly, when a hole leaves the p side, it leaves behind a stationary negatively charged acceptor ion. As the diffusion continues, a wall of positive ions builds up on the n side of the junction, and a wall of negative ions builds up on the p side. Because these stationary ions have been stripped of their mobile charge carriers, this interface region is now effectively empty of free electrons and holes. We call this the depletion region, or the space charge region. This exposed wall of positive and negative ions creates a strong, built-in electric field that points from the n side toward the p side. This electric field acts as a massive physical barrier. It begins to violently push back against the diffusion. If an electron on the n side tries to wander over to the p side, the negative ions repel it, and the electric field sweeps it back. This sweeping motion caused by the electric field creates a second type of current, called the drift current. The drift current flows in the exact opposite direction of the diffusion current. Very quickly, the device reaches a state of thermal equilibrium. At equilibrium, the diffusion current trying to push charges across the gradient is perfectly balanced by the drift current sweeping them back. The net current is zero. But we have successfully established a built-in electric field, which is the exact asymmetry we need to separate photo-generated charge. Let us visualize this on an energy band diagram. The most fundamental rule of a system in thermal equilibrium is that the Fermi level must be perfectly flat and continuous across the entire device. Because the Fermi level was near the conduction band in the n-type material, and near the valence band in the p-type material, forcing the Fermi level to be flat causes the actual energy bands to bend across the depletion region. This bending represents a built-in potential energy barrier. we can actually calculate this built-in potential mathematically. The built-in potential equals the thermal voltage, which is Boltzmann's constant times absolute temperature divided by the elementary charge, multiplied by the natural logarithm of the acceptor concentration times the donor concentration, divided by the intrinsic carrier concentration squared. Furthermore, we can calculate the exact physical width of this depletion region. The depletion width is the square root of 2 times the semiconductor's electrical permittivity divided by the elementary charge, multiplied by the sum of the acceptors and donors divided by their product, all multiplied by the built-in potential. When you build analytical models to simulate degradation mechanisms over time, tracking how this built-in potential and depletion width change as defects form in the perovskite layer is one of the most critical aspects of predicting device failure. Before we wrap up, we need to understand how this junction behaves when we apply an external voltage, putting it into a state of non-equilibrium. If we apply a positive voltage to the P side and a negative voltage to the N side, we create an external electric field that directly opposes the built-in electric field. This is called forward bias. The potential barrier shrinks, the depletion region narrows, and majority carriers flood across the junction, resulting in an exponential increase in current. If we reverse the battery, we add to the built-in field. This is reverse bias. The barrier grows taller, the depletion width expands, and virtually zero current flows. This rectifying behavior in the dark is described by the ideal diode equation. The current density equals the reverse saturation current density multiplied by the quantity of raised to the power of the elementary charge times the applied voltage, divided by the ideality factor, Boltzmann's constant, and temperature, all minus 1. To summarize, by doping our materials, we create a concentration gradient. The resulting diffusion of charges leaves behind stationary ions, which form a depletion region and a built-in electric field. This field bends the energy bands and creates the exact asymmetry required to separate charges. In our next lecture, we will finally turn the lights on. We will combine the optical physics from lecture 1.1 with the diode physics from today to see the true photovoltaic effect in action. I will see you in lecture 1.4.